Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is chapter 5.2, which is about area. All right, and before we talk about area, let's talk about something called sigma notation. And with sigma notation, what we're talking about is, well, if we use this capital letter sigma, that Greek letter sigma, and we started this way from I equals 1 to n of a sub I, what this means is we're adding a whole bunch of terms based on this a. And so that means I'm going to have a sub 1 plus a sub 2 plus a sub 3, so on and so forth until we get to a sub n. All right, in here, we have a couple of different things here. This I is our index of summation. Right, it represents, the I itself represents what values, where we're plugging in the values from 1 to n. This a sub I represents the ith term, right? The ith term of the summation. This n is, it's called the upper bound. So it tells us where we stop adding, how many terms we're going to have, right? And well, I guess I should say that this one represents the lower bound. And on this side over here, the rest of this, I mean, this is the actual expanded sum. And as I said, well, this symbol right there, that is the sigma. All right. All right, so that's just a whole bunch of terminology there. But how do we use this? So let's actually do an example. So let's say I have the summation from I equals 3 to 7 of I, right? And this in here, so my index is I. We're starting at 3, we're going up to 7. And what are we adding? I itself. So what does that mean? That means I'm going to have 3 plus 4 plus 5 plus 6 plus 7. All right. And in here, I mean, this adds up to 25, but that's not the point here. The point is, how does this become an expanded version? All right, that's sigma notation. Let's do another one. Let's say that I had something like the summation from I equals 1 to, no, not n, from I equals 1 to 5 of, let's say we have 3i, well, just 3i, right? So what does that mean? Well, we're going to put in 1 into here, into the I, so 3 times 1 is 3, plus, what's the next number? 2. 3 times 2, 6. Next number, 3. 3 times 3, 9. Next number is 4. 3 times 4 is 12. Next number, plug in 5. 3 times 5 is 15. And that's where I stopped because that was my upper bound, right? And again, here, well, that adds up to some value. Who cares? That's not the point right now. C. Let's say that we had the summation from I equals, let's start with 0 to 4 of something like, I don't know, I squared plus 2. All right, so let's see, plug in 0. 0 squared is 0 plus 2 is 2. Plus, plug in 1. 1 squared is 1 plus 2 is 3. Plug in 2, right? 2 squared is 4 plus 2 is 6. Plug in 3. 3 squared is 9 plus 2 is 11. Plug in 4. 4 squared is 16 plus 2 is 18. So there you go. That's I squared plus 2 being added over and over again from 0 to 4. All right. Cool. D. And I mean, the same idea, I mean, we can write whatever we want in here inside our index. And in fact, we can even use a different index. So we can do something like j from 1 to 3 of 1 over the square root of j. Right, and here, well, what do we do? We need to plug in the values 1, 2, and 3 into here. So we have 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3. Right? We can also do things like this. Like, let's do a little bit more generic. The summation from, let's do k equals 1 to n of 1 over n times, let's do k squared plus 1. Let's just do k squared. All right, and what does that do? Well, again, our index is k, excuse me. Our index is k. So we're only plugging things into k. This 1 over n stays 1 over n. So in other words, we can have 1 over n times 1 squared plus 1 over n times 2 squared plus 1 over n times 3 squared, so on and so forth until we get to 1 over n times n squared, whatever that is, right? And we can even do this a little bit more theoretical still. Let's say that we have the summation from I equals 1 to n of f of x of I times delta x. And what would this be? Well, this would be f of x of 1 times delta x plus f of x of 2 times delta x plus f of x of 3 times delta x, so on and so forth until we get to f of x of n times delta x. All right. So in general, that's how we work with this sigma notation. Now let's talk about a couple of properties of sigma notation. So some properties of summation. And these are the properties. If I have the summation from I equals 1 to n, well, in general here, it doesn't really matter what we're going from to. I'm just going to say this. So from using our index I, fine, I'll write it, of a constant times a sub I, well, this is the same thing as saying the constant times the summation of a sub I. So essentially, if our constant is not being affected by our index and is being multiplied into what is being affected by the index, we can just factor it out. Similarly, or actually a different property would be if I have the summation from I equals 1 to n of a sub I plus or minus b sub I. Right? In here, this just becomes the summation of each one of those separately. All right? So essentially, we can distribute this sigma over addition or subtraction. Right? So we can pull out a constant, and we can distribute the summation. All right. So those are some properties. Now, let's talk about some formulas, the summation formulas. If I have the summation from I equals 1 to n, and in here it's important that we actually are going from 1 to n, of just a constant, right? If we're just adding a constant over and over and over again, well, what does that mean? That means we end up with c plus c plus c, and many times, right? We're just adding c n times. And, well, think about it this way. If those were just a bunch of 3's, right? 3 plus 3 plus 3 plus 3, over and over again, well, what does that mean? It means that you're going to take the entire amount of them and multiply them by 3, right? In this case, we're going to multiply them by c. So we have just c times n, all right? Next one, if I have the summation from I equals 1 to n of just I, this actually depends on where we stop up here, right? It's going to be n times n plus 1 over 2, all right? So, and perhaps maybe I'll write the sum. So it's 1 plus 2 plus 3 all the way up until n. So that's n times n plus 1 over 2, right? If I have decimation of I squared, right, this is going to be, well, 1 squared plus 2 squared plus 3 squared all the way up until n squared. That's going to be n times n plus 1 times 2n plus 1 all over 6. And we'll do one more. The summation of I cubed. This is going to be, well, 1 cubed plus 2 cubed plus 3 cubed, so on and so forth, up until n cubed. That's going to be n squared times n plus 1 squared all over 4. All right. So let's see what we can do here with some of these. All right. And we're going to keep all of these in mind, all right, as we go through the next couple of examples. So, example G. Let's say that we have the summation from I equals 1 to n of I plus 7 over n squared. All right. In here, well, let's notice something. This n squared is not being at all affected by the index, and we can pull it out, right? It's really 1 over n squared. So I can pull out at 1 over n squared, and we have the summation from I equals 1 to n of I plus 7. But we know that this sigma can actually be distributed over addition, so this becomes 1 over n squared times the summation of I plus the summation of 7. And obviously from 1 to n on each of those. And at that point, well, we know what these summations are. Right in here, I'm adding I over and over again. So when we do that, that was n times n plus 1 over 2 plus, we're adding 7 over and over again. We know what that was. That was 7n. All right. And if I distribute this 1 over n, actually, you know what? Let's come up with a common denominator here inside first. So I have 1 over n squared times, the common denominator would be 2. This numerator is already over 2, so I'm just going to distribute that n. So I have n squared plus n plus. This has a denominator of 1, so to go from 1 to 2, multiply by 2, so I have 14n. And that simplifies to, well, n plus 14n is 15n, so I have 1 over n squared times n squared plus 15n over 2, right? And then I can factor an n from the numerator here, and I end up with n times n plus 15 over n squared times 2 is 2n squared. Reducing this n with one of those, I end up with n plus 15 over 2n. All right, so now, let's see what we would get if we had different values of n up here, right? So for example, if I had n being equal to 10, what would this become? Well, I end up with 10 plus 15 over 2n, over 2 times 10, giving me, well, 10 plus 15 is 25, 2 times 10 is 20. These are both divisible by 5, so I end up with 5 quarters. All right, cool. What if n was 100? Well, I would end up with 100 plus 15 over 2 times 100, giving me 115 over 200, right? And in here, that simplifies to be, well, let's see, 115 divided by 5, that's 23, and 200 divided by 5, that's 40. And what if n was 1,000? Well, we have 1,000 plus 15 over 2 times 1,000, giving us, well, 1,015 over 2,000. Dividing that by 5, right, because they're both divisible by 5, what does that give us? This gives us 203 over 400, all right? And I mean, we could continue to do that over and over again, right? Make bigger values here of n, But what if n was going to infinity? So what if n was going to infinity? So what would that do? That would give us that this summation, right, from I equals 1 to n of I plus 7 over n squared. Well, since n is going to infinity, what we really should do here is write the limit as n goes to infinity in the front of it. And that would give us, well, the limit as n goes to infinity of, we already know what they simplified to, right? N plus 15 over 2n. So n plus 15 over 2n. And as n goes to infinity, well, what can we do here? If I multiply this by 1 over n over 1 over n, right? That fraction is just equal to 1. What I get here is the limit as n goes to infinity of 1 plus 15 over n over 2. And as n goes to infinity, this entire thing, that piece right there, 15 over n, goes to 0. So we end up with 1/2. So what I'm getting at here is that this summation, I mean, depending on the values of n, we obviously get different terms, right? But look at this. And here we're saying we're going to have infinitely many terms. And with those infinitely many terms, this sum just ends up becoming 1/2. All right, closer and closer to 1/2 there. So now, next thing, let's talk about area, all right, because that was all just segment notation. So let's talk about area. And in here, when we say area, what we mean is under a curve, the area below a curve, right? So for example, let's say that I had this following function, all right? So there's my x and y axis, and let's say I had something like that, right? And what I want to do here is figure out, let's say here's A, here's B. I want to figure out this area inside here, right? And well, how would we do that? Notice that this is not a nice shape, right? We know the areas of a whole bunch of nice shapes, right? Like squares and rectangles, triangles, circles, so on and so forth. But how will we find the area of this shape? Well, what we can do here is we can approximate this, right? And by that I mean, well, we can approximate it using rectangles. So for example, I can use this rectangle, right? And then add this rectangle, and then the next rectangle, so on and so forth, right? But notice that every single rectangle here that I'm drawing, they're all below the curve, right? So in here, the sum of all these rectangles would be an underestimate, all right? Now, oh, that's not what I want to do. Let's copy this. There we go. If instead of having all those rectangles being below the curve, what if they were above the curve, right? So let's get rid of all those little lines there. Because what we can do here is think about it this way, and perhaps I'll do it in red. If I start drawing all these rectangles that are slightly above the curve, this is going to be an overestimate, right? Because the area of all those rectangles will be bigger than the actual area below the curve, right? So now, this leads us to the next idea. This up here, this estimate on the top, and perhaps let me shift this a little bit higher so I can flip both of them in the screen. All right. This top one, we're going to call that the lower sum, or the lower estimate. The lower sum. And in here we're talking about the estimate of the area. Whereas this bottom one, we're going to call it the upper sum. Right? Now, the next thing we want to figure out here is, well, what would the formulas for these things be? How would I find such an estimate, right? Well, let's think about this. We're adding a whole bunch of rectangles, right? So if I look at just one of these rectangles, perhaps I'll erase a couple of the ones near it. So let's say I'm talking about specifically this rectangle right here, right? And in here, this interval from A to B, let's say that we split it up into n pieces, right? Or maybe I should say n intervals. All right. And I'm going to erase a couple of more of these. In this rectangle, well, this is the height, right? And this is the width. I'm going to call that width delta x, all right? And the height, well, the height, it's based off of the actual value here of that function at this spot, right? In this interval, this spot right here, that value, is the x value that produces the smallest value throughout the function. So I'm going to say that this is just f of lowercase m sub I, all right, because where m sub I is the minimum value, all right. So here we're saying m sub I is the value of x that corresponds, or maybe we'll write it as such that value of x such that f of x is the smallest, or is a minimum on the interval. And well, what would the area of that rectangle be? Well, the area would be just the length times width, right? In general, for rectangles, the area is length times width. And what would be the length? The length is this height here, and the width is this delta x. So that would be f of m sub I, lowercase m sub I, times delta x. So that's just one of them. But if I have n of them, and many, well, this lower sum, the estimated area, so it would be the summation. Maybe I'll write this. Lower sum. We're going to write it as lowercase s of n, right, because there's n many of them. It would be the summation from I equals 1 to n of f of m sub I delta x, and again using lowercase m. The upper sum would be very similar, right? It's going to be essentially the same idea. So perhaps I'll just keep the same exact rectangle there, or the one that corresponded to the same piece on the drawing. And we're talking about this rectangle now. This is still going to be split up into n intervals. This is still just the width of delta x. But now, this length or the height here of this rectangle, I'm going to call it f of capital M sub I. All right? And in here, we're going to have a similar definition for that M sub I. So M sub I, capital M sub I, is the value of x such that f of m sub I, and perhaps I should have said here f of m sub I, lowercase m sub I there. All right, cool. Capital F of m sub I, excuse me, f of capital M sub I, there we go, is a max on the interval. So, well, we already know what the area formula is here, so right? So for this specific rectangle, the area, which is again this length times width, would be equal to f of capital M sub I times delta x. So our upper sum or upper estimate, I'm going to call it capital S of n, and it's going to be the summation from I equals 1 to n, right? Because we're going to be adding a whole bunch of rectangles, and many of them, of this area, f of m sub I times its width. All right. Now, in here, it turns out that the true area, that the actual area of that region is somewhere between the lower sum and the upper sum, right? Because again, the lower sum was underestimates, whereas the upper sum were overestimates. So let's look at an example for this. All right. So the instructions here are find the lower and upper sums of the area on the given interval. All right, so let's see. Let's say that I have f of x being the square root of x. And the interval we're going to be working with is from 0 to 1. And let's do 4 intervals using n equals 4, right? N is 4 intervals. Now, one thing I should have defined here is how do we find this delta x? So let's define that right now. Well, let's think about this. We're doing the interval from a all the way to b, right? So that entire distance, we're splitting it up into n pieces. Well, how will that work here? Well, the entire distance from a to b is the big value minus the smaller value, and we're splitting it up into how many pieces? N. So delta x in general is just b minus a over n. All right, so now let's see how that applies here. This n being 4, that right away tells me that delta x is equal to, well, 1 minus 0 over 4, which is 1/4, right? And now, well, let's see how we're going to find the upper and lower sums here. So let's draw this function. What does it look like? That's what that function looks like, right? That's the square root of x. And let's say here that, well, around here, let's say this is 1 and this is 0. So 1 here is the area underneath this curve, right? And we're going to start by approximating it. So I'll do the lower sum first. I'm splitting it up into 4 different intervals, right? The width of each of these intervals is delta x, which is 1/4. So to go from here to here, add 1/4. This value right here is 1/4. To go from here to here, add 1/4. That value is 1/2 now, right? Because 1/4 plus 1/4 is 1/2. And this one over here is 3/4, and then 3/4 plus 1/4 is 1. Good. Now, what did the lower rectangles look like? What the lower estimates? Well, in this interval, this first interval right here, the value of x such that the function is the minimum is here. So this is the rectangle. That's kind of weird because it's just a height of 0, but we'll think about that later. Now, in this next interval, from here to here, what is the smaller value? Well, it's here. So this is going to be the rectangle that we're going to be adding. In this next interval, what is the smaller value? Well, it's the one on the left side here, right? So this is the rectangle, and we're concerned with this value. And in this last one, this is the rectangle, right? And in there, well, how are we going to do this? Well, let's see. So we're saying that our sum, our lower sum, we already had a formula for it, right? The summation from I equals 1 to n of f of lowercase m sub I delta x. All right. What does that mean here? Well, delta x, we already know to be 1/4. The values that we're going to be plugging in are here. So we have f of 0 times 1/4 plus, maybe I'll put the 1/4 in the front. 1/4 times f of 0 plus 1/4 times f of 1/4 plus 1/4 times f of 1/2 plus 1/4 times f of 3/4. And now, they'll have a 1/4, so I'm going to factor that out. So I have 1/4 times f of 0. Well, our function was the square root of x, right? So we're just taking square roots. So the square root of 0 is 0, plus f of 1/4. The square root of 1/4 is 1/2, plus the square root of 1/2, I'm just going to write it as 1 over radical 2, plus the square root of 3/4, I'm going to write it as radical 3 over 2, right? And that ends up being our answer. Now we can rewrite this really in, if I rationalize this 1 over radical 2, this is really radical 2 over 2. And now everything has a denominator of 2, so I can write this as 1/4 times 1 plus radical 2 plus radical 3, all of that over 2, right? And that gives me approximately 0.5183. That's a calculator answer, right? But this is what we end up with. Now that's the lower estimate. Let's figure out the upper estimate, or the upper sum, right? So let me just go ahead and copy this so we can get a visual for that. All right, there it is. But we need to update this because all these rectangles were lower sums. So we're gonna get rid of a lot of these things. All right, we're still splitting up the interval into 4 pieces, so those values are still the same. But now, let's look at the upper sums. In this region, in that first interval, this value is the highest value of that function. So this is the rectangle that we're concerned with. And this one, this is the point up here, right? So this is the rectangle, and the next one, it's this rectangle. The last one, it's this rectangle, right? So we already know what the formula is here. We're going to say, so capital S sub n, right? Because this is our upper sum. It's going to be the summation from n equals 1, from I equals 1 to n of f of capital M sub I delta x. We already know what delta x was, right? It's still 1/4. And now, what does this give us? So we're going to have 1/4 times, in this first interval, this 1/4 here is what gives us the bigger value. So we're going to have f of 1/4, right? Because capital M represents the value of x that gives us the maximum value of the function on the interval. All right, plus the next one, 1/4 times f of 1/2, plus 1/4 times f of 3/4, plus 1/4 times f of 1. All right. And again, they all have a 1/4 on there, right? They're all being multiplied by 1/4. So we can factor out a 1/4, and we're left with, well, f of 1/4. So we're taking square root. The square root of 1/4, 1/2, plus the square root of 1/2. Well, we already saw that it becomes radical 2 over 2, right? Plus the square root of 3/4, radical 3 over 2, plus the square root of 1 is just 1. But I'm going to write that 1 as 2 over 2, right? Because 2 over 2 is just 1. And at this point, well, what do we actually get? I end up with 1/4 times common denominator of 2. And I'm going to write this as 3, right? 1/2 plus 2/2, that's 3. So 3 plus radical 2 plus radical 3. And in here, this is approximately 0.7683. And that was supposed to be an 8. There we go. 0.7683. And well, what do we find here? Well, what we found here overall is that the true area is somewhere between, what was our lower sum? 0.5183 and 0.7683. Somewhere in between those. Now, we do have ways of finding the true area, right? We'll discuss that later. But I will tell you here that the area, the actual area, is 2/3, which happens to be 0.6 repeating. And 0.6 repeating is definitely between 0.5 and 0.7, right? So there you go. Now, I want to make a note here, right? Or at least I want to state something. Notice that in this function, the lower values were always on the left and the upper values were always on the right. That's not necessarily true for each case, right? It depends what the function looks like. So what do I mean? So let's say, so note, lowercase m sub I and uppercase m sub I depend on the function. And what do we mean by that? Well, let's say that we had this. Let's say that I had this function, or this curve, something like that, right? And I'm going to split this up from here. Here's A, and here is B. And well, if I look at this first, the first interval here, the overestimate depends on the left part of the interval. But over here, excuse me, I said lower estimate, I meant upper estimate. The upper estimate depends on the left part, but over here, the upper estimate depends on the right end of the interval, right up here. So we have to be careful about that. We have to actually see, well, if you really want the lower estimate or the lower sum, you have to look at where things are, right? And similarly, in here, in the next interval here, so that was for the upper estimates. For the lower estimate, here it depends on the right part of the interval, but over here, it depends on the left part of the interval. All right, so we have to be really careful with that. All right. Now, another way to estimate some of these is using the midpoint rule. So let's see what the midpoint rule is. The midpoint rule is, well, let's look at it visually first. And I'll do the same visual as we had. Oh, that's not the visual I wanted. I'll just redraw another one. If I had this curve, right? And again, we're trying to figure out stuff from, well, let's exaggerate that curve a little bit. There we go. From A to B, right? What we can do is, for example, let's split this. Let's look at this first interval, right? And in here, this is going here this way, and all the way up there. Now, clearly, the lower sum is, I mean, the lower estimate would be using this point over here. The upper estimate would be using this point over here. But the midpoint, what we can do is use the value right in the middle of that interval to build our rectangle, right? And what do I mean by that? That means we're going to use this point to build this rectangle, all right? Notice that depending on the function, we're actually kind of closer in. So essentially, we're doing both an over and an underestimate depending on where the value is, right? So over here, let's say that the next point here. So if I'm gonna do this entire interval here, all right, we're gonna base it off of the midpoint. Perhaps I'll specifically point out where the intervals are in blue, and then in yellow, I'll do where the midpoints are. And I guess I'll stop here. That would be our B value. So our midpoint here, this right here represents the height. So we're using this rectangle. In the next one, we're going to use this value. So we're going to use this rectangle. Right? In the next one, we're going to use this value. So this rectangle. And then this value. So that rectangle. All right. So again, we're using the midpoints of each interval to figure out what our height's going to be. We're still defining this width to just be delta x, but now we're defining our height differently. Now, how do we do that? How do we actually figure out what the midpoints are? Well, let's think about it this way. How do we find the number exactly between two numbers? All right. So for example, if I had the number 10 and the number 20, what is the number in between those? Exactly in between those, it would be 15. How did I get 15? Well, the average between 10 and 20 is 15. So that's what we're going to do. We're going to do the average. So for example, if we're talking about here, one of these being the ith interval, right? This is the first, second, whatever, so on and so forth. So for the ith interval, the midpoint, which I won't give it any notation for it, just say what the midpoint is. The midpoint is going to be found by doing x sub I minus 1 plus x sub I over 2, where x sub I is the left point of the interval, where x sub I minus 1 is the left point of the interval, and x sub I is the right point of the interval. Right, so in here, the area, using the midpoint formula, the area would be approximately the summation from I equals 1 to n of f of x sub I minus 1 plus x sub I over 2 times delta x. And delta x still defined the same way, right? B minus a over n. So let's see. What letter am I at? Was the last one H? I think it was H. Yeah, so I. Sorry about the scrolling. All right, so I. Let's say estimate the area under the curve of f of x is equal to sine of x on the interval from 0 to pi using 4 intervals. So with n being equal to 4. And well, what is that going to do for us? Well, let's look at the visual here. All right. What does sine look like? Well, it looks as follows. Something like this. Oh. Right, so on and so forth. It repeats forever and ever. Both ways. This point right here, that's pi. So what we want to do here is we want to split up this interval into 4 pieces, and then we're going to use the midpoint formula. So I should have specified there in the instructions using the midpoints. All right, so we've got the interval from 0 to pi. We're doing 4 intervals. So let's see what that means. That means that we're gonna say, well, this is split up here, here, and here. And what are those values? Well, let's figure out what delta x is then. So delta x would be, well, we know is b minus a over n. And in this case, our b is pi. So we have pi minus a, our a is 0, over n, which is 4. So that's pi over 4. All right, so to go from here to here, that's pi over 4. The next one, add another pi over 4. We're at pi over 2. The next one, add another pi over 4. We're at 3 pi over 4. Add another pi over 4. We're at pi. All right, so I'll just make these dotted lines here to show where the intervals are ending. But now, let's do the midpoints, right? Because we're trying to do the midpoints. So in here, this is the midpoint, that being pi over 8, right, between 0 and pi over 4. And the rectangle that we're going to be looking at is this rectangle. In the next interval, the rectangle that we're going to be looking at, based out of the midpoint, would be this rectangle. In the next interval, it would be this rectangle. Well, really, those should be the same, because we have sign is symmetric there. And then in the last one here, it should be about the same as that first one. There we go. So those are all the midpoints. But now where are they? So this is pi over 8. This one right here is 3 pi over 8. This one right here is 5 pi over 8. And this last one over here is 7 pi over 8. All right? Cool. Now, let's see. Our area is going to be, well, the summation from I equals 1 to n of x of f of x sub I, f of x sub I minus 1 plus x sub I over 2, right, the average of the two, times delta x. And what does that mean in this case? Delta x we know to be 1/4. This is going to be pi over 4, right? Pi over 4. And, well, what is that going to be? So f of that value, so we're going to have sine of our midpoint being pi over 8, and then that times pi over 4, plus the next midpoint, 3 pi over 8. So sine of 3 pi over 8 times pi over 4, plus the next midpoint, 5 pi over 8, sine of 5 pi over 8 times 3 times pi over 4. That's a 5 there. And then plus, lastly, 7 pi over 8. So sine of 7 pi over 8 times pi over 4. I mean, they all have a pi over 4, so if we really wanted to, we can factor that out, right? So I end up with pi over 4 times sine of pi over 8 plus sine of 3 pi over 8 plus sine of 5 pi over 8 plus sine of 7 pi over 8. And if you plug that into the calculator, that ends up being approximately 2.052. All right, that ends up being approximately 2.052. I will tell you here that the true area, so the actual area, is 2. So 2.052, pretty close estimate. All right, we're less than 5/100ths off. So now, we just discussed the lower sum, the upper sum, or the lower estimate, upper estimate, as well as the midpoint estimate, right? And, well, how do we actually find the true area, all right? Well, the idea is simple. So, let's see. So let's define the actual area here. Definition for the area of a region on a plane. So the area is going to be, well, first let me actually put a visual in here. And we're going to try to get something similar as before. So something like that. And let's exaggerate it. There we go. Way better. And we're going from A to B. Right? And how are we going to find the true area of this? Well, let's think about it this way. When we started doing this, we spoke about putting a whole bunch of rectangles, right? And we split this up into n intervals, right? So, for example, if I had 4 intervals, well, there's one interval. If I had 2 intervals, well, I split it up into those 2 big rectangles there. If I had 4 intervals, we split it up into the 4 rectangles corresponding to that, right? But if I had 8 intervals, we split it up into this, here, here, and here. If I had 16 intervals, we split it up here, here, so on and so forth. So what's my point here? My point here is that the more rectangles that we do here, the closer our actual estimates end up being, right? And notice here I'm doing all the lower rectangles. But now let's look at all the upper rectangles. Well, they're going to be very similar, right? But instead of, they're going to be this. And what I want you to notice here is that these upper estimates, the rectangles on top, they're very, very close to the lower estimates, right? And in fact, I mean, this was just with 16 intervals, but if we did 32 intervals, those values, the lower rectangles and the upper rectangles, are going to be closer in height, right? What do I mean by that? Let's say, for example, we zoom in into here, and perhaps I'll do that in a different color. Let's zoom in into here, right? And what does that look like? Well, we had a curve there, right? And we had the lower estimate being something like that, right? And the upper estimate being something like this, right? And in here, if we were to split this interval again, well, what would that look like? Let's say if I split it up in half, well, then this would give me the upper estimate, and then this would give me the lower estimates, right? The rectangles associated there. But notice that that became closer. Those values on the top and bottom, they became closer. And if I split it up again, we're going to get even closer and closer to the point that the true area is somewhere in between the upper estimate and the lower estimate. So what we're going to say here is the actual definition here for the area is going to be the summation, well, the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I star times delta x. Now, let's explore what this is saying. The limit as n goes to infinity. Remember that n is the amount of intervals, and the amount of intervals represents how many rectangles we're using. So what we're saying here is we're going to put infinitely many rectangles in here. Right? Infinitely many rectangles in here, essentially so that the width of them becomes 0. X sub I, delta x is still defined the same exact way. Delta x is still b minus a over n. But what is x sub I star? X sub I star is just any point on the ith interval, so a representative point on the ith interval. And what does that mean? Well, that x sub I can represent the point that makes the rectangle the lower value, or the upper value, right, for the lower sum or the upper sum, or the midpoint, or the left end point, or the right end point, or any point in this interval, right? In general, rather than work with upper and lower estimates, or the midpoint, we try to work with either the left or the right endpoint. And if we were doing the right endpoint, x sub I star can be written as a plus I delta x. What is that saying? Well, let's see. This point right here, if I'm starting here, this is in my first interval, right? The right endpoint, actually, so I colored the wrong one. The right endpoint, well, let's look at this interval. The right endpoint is here, right? And how do I find that value? Well, I'm starting at A, and I'm adding, well, if it's, what interval is that? 1, 2, 3, 4, 5, 6, 7. We're in the 7th interval. So I'm going to multiply that delta x, the width here, times 7, and add it to A. That's how I get to there. So those are the right endpoints. We also have left endpoints. The left endpoints can be defined by letting x sub I star be equal to b minus I delta x. And essentially there, we're working in a similar way, right? So if I'm looking at this for the left endpoint, we're starting at b, and we're subtracting delta x many of them, right, from B. In general, I would recommend that unless otherwise stated, you use the right endpoint. So unless the actual instructions say to use the left endpoint or to use the midpoint or to use the upper sum or the lower sum, I would recommend you stick with using the right endpoint there. All right. And again, this piece right here just represents the area of one of those rectangles. So let's do an example here. Let's do an example. I think I'm at J. Example J. So let's find the area of the region. I'll just find the area. I'll just leave it as that. And what we mean is the area of the region bounded by this stuff. So find the area of f of x being x cubed, and so we're looking at that on the interval from 0 to 1, right? So let's get a visual as to what we're talking about here. I'll lower this a little bit. X cubed looks something like this, right? And we're trying to go from 0 to 1. So let's say that this right here is 1. And what we're finding here is this region, this area inside here, right? This little wedge that kind of looks like a triangle, but it's not a triangle, right? We're trying to find the area of that little wedge here. And how are we going to do it? Well, let's look at a representative rectangle here, because that's what we're going to be adding over and over and over again, right? Our width here is delta x. Our height here, well, if I use, well, in general, it's just f of x, right? So what are we going to do here? Well, our area is going to be equal to the limit as n goes to infinity, because we want infinitely many rectangles, of the summation from I equals 1 to n of our function of f of x delta x. Now, what is delta x? In here, delta x is equal to b minus a over n. In this case, that's 1 minus 0 over n, which happens to be 1 over n. Notice that I'm leaving it as n because, well, n is going to go to infinity, so we can't actually plug in any value there. Now, let's look at the right endpoints. And in here, I'll put it on the bottom that we're doing right endpoints. And we know that the formula was a plus I delta x. So in this case, a is 0, so 0 plus I times delta x. Delta x is 1 over n. So really, I end up with I over n, right? And now, let's see what that does for us. Our area now is, well, the limit as n goes to infinity of the summation from I equals 1 to n of our function, plugging in our x of I, and right, I should have said x of I star here, right? X of I star, so I have f of in times delta x, which was 1 over n. Notice that this 1 over n is not at all being affected by the index, right? The index of summation, right? The index is I. So this 1 over n is not being affected. So I'm going to put it all the way on the outside. And in fact, I can put it on the outside of the summation, but not on the outside of the limit, because the limit does affect the n. So I'm going to write it as the limit as n goes to infinity of 1 over n times the summation from I equals 1 to n of f of I over n. But what was f? F was x cubed. So what I really have there is I over n cubed, right? So now, at that point, we're going to say, well, this becomes the limit as n goes to infinity of I over n times, well, the summation of I cubed over n cubed from I equals 1 to n, right? And what does that do for us? Well, this n cubed is not being affected by this index here, so we can pull that out here. So we really have the limit as n goes to infinity of 1 over n to the fourth times the summation from I equals 1 to n of I cubed. But we had a formula for this, right? We had a formula for this, for that summation from I to n of I cubed. And that formula was, well, so we have the limit as n goes to infinity of 1 over n to the fourth times n squared times n plus 1 squared over 2, right? That was our formula for I cubed. And well, what does that do for us? Well, let's see. Since we're taking the limit as n goes to infinity, we want to expand this a little bit, right? So in here, in the numerator, well, let's see, this n squared cancels out 2 of these. So what I really have here is the limit as n goes to infinity of n plus 1 squared. N plus 1 squared is n squared plus 2n plus 1 over. On the bottom here, I have n squared. N squared times 2 is 2n squared, right? If I multiply this by 1 over n squared over 1 over n squared, this gives me now the limit as n goes to infinity, and that's an infinity symbol there. Not any better. There we go. Distribute this 1 over n squared into each of these. 1 plus 2 over n plus 1 over n squared over 2. And as n goes to infinity, this piece goes to 0, that piece goes to 0. So overall here, I end up with 1/2. Wait, hold on a second. I made a mistake here. Look at this. That formula wasn't over 2, it was over 4. So I'll put it in blue here so you see where my mistake is. So that 2 should be a 4. This 2 should be a 4. And there we go. This 2 over here should also be a 4. There we go, 1/4. All right. So the area is 1/4. The process was correct. I just used a slightly wrong formula. It's over 4, not over 2. All right, so there we go. We find the total area there, the area of that wedge there. All right, 1/4. Now, let's do another example. So that was J. So K. So let's find the area beneath the curve of f of x equals, let's complicate this a little bit. Let's do 4 minus x squared, and then we're going to do the interval from 1 to 2. All right. All right, so let's get a visual as to what this is so that we can see what's going on here. 4 minus x squared. Well, what does that look like? That's a parabola facing downwards, shifted up by 4 units, right? So let's say that it looks something like this. And perhaps I'll lower this a little bit more. It looks something like this, right? But we're going from 1 to 2. So we're doing this piece right here. From 1 to 2. That value there is 2. And we're trying to figure out what this area is here, right? Well, we already know the formula. The formula was that the area is equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of x of I star times delta x. And again, we know that delta x is just b minus a over n. And if I use the right endpoints again, and again, in general, I do recommend using the right endpoints unless the instructions say otherwise. So using the right endpoints here, I'm going to say that that's a plus I delta x, right? So what does that mean? Well, let's figure it out. What's delta x? B minus a over n. So 2 minus 1 over n, which gives us 1 over n. And x of I star, what is that? X of I star. Well, that's a, which was 1, plus I delta x, so I times 1 over n. I'll just write this as 1 plus I over n. All right. Now, that right there is our setup. Let's actually find the area. Well, so our area is going to be the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I. X sub I was our radian point, so I have f of 1 plus I over n times delta x, and our delta x was just 1 over n. All right. Now in here, our 1 over n, that's still not being affected by the index, right? So we can still factor that out just like we did in the previous example. So we have the limit as n goes to infinity of 1 over n times the summation from I equals 1 to n of, well, what was our formula? What was our function? 4 minus x squared. So in here, I'm going to have 4 minus 1 plus I over n squared, right? And now let's see what we can do there. Let's simplify that a little bit. All right. And perhaps I'll do some of that on the side over here for this piece. So I have 1 plus I over n squared. Well, what does that look like? Well, recall that if I have a plus b squared, that's just a squared plus 2ab plus b squared. In this case, what does that mean? That's going to mean our a is 1, our b is I over n. So I end up with 1 squared plus 2 times 1 times I over n plus I over n squared, right? A squared plus 2ab plus b squared, which is just 1 plus 2I over n plus I squared over n squared. All right, so that's just this piece right here. So let's go ahead and write that in there. So we have now the limit as n goes to infinity of 1 over n times the summation from I equals 1 to n of 4 minus that entire thing. 1 plus 2I over n plus I squared over n squared. If I distribute this negative into each of these, we'll end up with 4 minus 1. 4 minus 1 is 3, so I can write this as a limit as n goes to infinity of 1 over n times the summation from I equals 1 to n of 3 minus 2I over n minus I squared over n squared. All right. And at that point, well, I've got a summation of a bunch of stuff there. We know that we can distribute the summation into each of those. So what we have is the limit as n goes to infinity of I over n times the summation of 3 minus this 2 over n is not going to be affected by the index. So I'm going to write it as 2 over n times the summation of I minus this n squared is not being affected by the index. So I'm going to write it as 1 over n squared times the summation of I squared, right? And at that point, well, we have formulas for each one of those. We have the summation of a constant, the summation of I, the summation of I squared. So what we can do here is, let's see, the limit as n goes to infinity of 1 over n times the summation of 3 is just 3n, right, when we're going from 1 to n, minus this 2 over n is still there. The summation of I, that was n times n plus 1 over 2, minus this 1 over n squared is still there. The summation of I squared, that was n times n plus 1 times 2n plus 1 over 6, right? And at that point, well, let's see what we can do. Let's distribute, let's reduce, let's see what let's do as much as possible here. This n cancels out that n. This 2 cancels out that 2. This n reduces this n. And that's pretty much it so far. Let's distribute this 1 over n now. So I end up with the limit as n goes to infinity of 1 over n times 3n is just 3, minus 1 over n times n plus 1, excuse me, so we have n plus 1 over n, minus 1 over n times 1 over n is n squared, and then that times 6 is 6n squared, And on top here, I still have that n plus 1 times 2n plus 1. Let's actually expand that. N times 2n is 2n squared. N times 1 is n. 1 times 2n is 2n. So combined, they're 3n. And then 1 times 1 is 1. And we're taking the limit as n goes to infinity, right? And in here, what we can do is we can apply the limit to each of those pieces separately, right? But what I'm going to do here is I'm going to multiply this one by 1 over n over 1 over n. And I'm going to multiply this by 1 over n squared over 1 over n squared. The reason I'm doing that is so that we can rewrite this as limit as n goes to infinity of 3 minus 1 plus 1 over n over 1 minus 2 plus 3 over n plus 1 over n squared over 6. And as n goes to infinity, this piece goes to 0, this piece goes to 0, this piece goes to 0. So what we get now is, well, the limit as n goes to infinity, well, all the n's are gone, right? We already took the limit, so I end up with 3 minus 1 minus 2/6. 2/6 is just 1/3, right? And what is that? So 3 minus 1 is 2, so we have 2 minus 1/3, right? Common denominator is 3, so I have 6 minus 1 over 3, giving me 5/3, right? So the area beneath the curve over here, that's just 5/3, all right? Units squared, right? Because it's an area, but it's just 5/3. Now, I do want to make one last point here before I end this lecture, all right? In general, and perhaps I'll do this in yellow. Whenever we're doing the limit as n goes to infinity of the summation from n equals, well, let's do it this way, of I of 1 over n from n equals 1 to n of I squared. Well, let's do this. I'm going to do it for the constant rule. I'm going to do it for just I. And I'm going to do it, well, I'll do it for all those three formulas that we spoke about. But notice I'm multiplying by 1 over n here. So these are slightly different from what we had in all the other ones. From I squared. And lastly, for I cubed. All right. Well, in here, we already know what the summation from 1 to n becomes. So in here, I end up with the limit as n goes to infinity of 1 over n times Cn. Here, these n's cancel out, so I end up with just C. Next one, I end up with the limit as n goes to infinity of 1 over n times the summation of I. The summation of I was n times n plus 1 over 2, right? And I just realized that this is not what I meant. Let's fix how I meant this. So the first one's fine, but I messed up in all of these. What I want to talk about here is the summation of I over n, the summation of I over n squared, and the summation of I over n cubed. All right, and all of this times 1 over n. So what does that give us? All right, so this n on the bottom can be factored to the outside, so I have the limit as n goes to infinity of 1 over n squared times the summation of I, right? And the summation of I, we already know what it is, so I have the limit as n goes to infinity of 1 over n squared times n plus 1 over 2. This will always go to 1/2. Always, all right? And I'll let you figure out the steps in between there. But essentially distribute this n squared, multiply both the top and bottom by 1 over n squared. All right, in here, what we really have here is, well, I squared over n squared. Take the n squared to the outside, and I end up with 1 over n cubed times the summation of I squared, right? And we're going from 1 to n. And the summation of I squared, we already know what it is. So we have the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2n plus 1 over 6. This piece, when we have 1 over n cubed with that will always go to 1/3. And again, I'll let you figure out the step in between. Essentially, distribute the entire top and multiply the top and bottom by 1 over n cubed. And in here, the limit as n goes to infinity of 1 over, well, let's see, I cubed over n cubed. This n cubed can be taken out to the outside, so I have 1 over n to the 4th of the summation from I equals 1 to n of I cubed, which gives me the limit as n goes to infinity of 1 over n to the 4th times the summation of I cubed. Remember, there was n squared times n plus 1 squared over 4. This would always go to 1/4. All right. So being able to recall these will save you some time in doing these long summation problems. All right. All right. I'll end this. Yeah. So that's the end of 5.2. All right. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.